Hello, everybody. Today we're going to be talking about chapter 3.1, which is about temperature. So now we've reached the point where we can start thinking about temperature better. We can better define it, and we can analyze what exactly it does. We have also introduced already the entropy, which we said is equals to K ln of the multiplicity, and uh, we're going to plot the entropy against the units of energy. So I'm gonna say that we have QA on the x-axis and the entropy S on the y-axis. So as our QA increases, our S of A increases. So we're gonna have something like this, something that reminds of a um, of a natural logarithm function. And then when we have our QA increasing, our SB will be decreasing. Okay, so I'm gonna start down here. Oops. I want to do well because then we can talk about it. Okay. Now we're thinking about a two-Einstein solid with Na being equals to 300 and Nb equals to 200. And we said this one was SB. So we're gonna have an S total that has this kind of shape. Not very good at drawing. Didn't pursue a degree in art. Anyhow, turn off. It's true. Okay. So now that we have this, we can analyze. Oh, this is S total. S total versus that's not versus QA. However, we know that QA and the energy of A are directly correlated. So whether we write QA or UA, so total energy of A, is the same thing. So it's like we plotted S total versus U of A, or again S A versus U of A. So that's what we plotted. And SB versus the U of B. Okay? So now what we want to find is a point where the change in entropy is equal to zero. So when we have a flat piece, where we're going to have something somewhere around here, that means that our uh, derivative of S total in terms of, again, we can write QA or we can write UA is equals to zero. And we know that S total is equals to SA plus SB. Therefore, we're saying that the derivative of SA plus SB over U derivative of UA in terms of UA, sorry, is equal to zero. So we can break this in pieces. We can say derivative of SOA in terms of U of A plus derivative of S of B in terms of UA is equal to zero. Now, let me look back at the graph so we can talk about it. So this point right here that I called in red is going to be this point right here for S of A and this point right here for S of B. Now, as you can see, one of them is pointing up, one of them is pointing down. So one of them has positive slope and one of them has negative slope. In fact, if we add them together, we should obtain for these two pieces, if we add them together, we should obtain something like zero. Okay? Now, I want to say that then derivative of S of A has to be equals, in terms of U of A, has to be equals to negative derivative of S of B in terms of U of A. However, let's go back. We know that Q of A increases in the right direction. However, Q of B increases in the negative direction, the left direction. So instead of talking about, sorry, you know what? Let's see. No, we're gonna have a Q total. Is gonna be equals to QA plus QB, and so QB is gonna be equals to Q total minus QA. Okay. Now let's ignore these Q total because we don't. Let's still keep the minus because we're talking about a graph, so there's not gonna be a constant anywhere. Therefore, our UB is gonna be equals to negative U of A, or negative UB is equals to UA. So let's go back and plug it in our value here. We're gonna have, let me take this and bring it over here so we have more space. That derivative of S of A in terms of U of A is equals to negative derivative of S of B in terms of, now we'll switch this, negative U of B. That's what we said over here. We substituted. So what we get is derivative of S of A over U of A is equals to derivative of S of B over U of B. And as you can see, this makes sense because I just took the negative out, and with this the negative, it makes a positive. So when we have these two being equal, we are at an equilibrium. Okay? So when these two are together, we have an equilibrium. Okay, so now it wants us to look at the values, the units of. I'm gonna just take the right side for now. We're gonna have for S of A, the units are joules over Kelvin, and for the units of, write this better, okay, U of A, we have, of course, joules. So here we're gonna have, talking about the units of measure, joules over Kelvin over joules. So here we have, and so this out, we're gonna have 1 over Kelvin. And this is gonna be equals to 1 over temperature, because we know the temperature is equals to Kelvin. So we can say, and in this case, of course, it would be A. So we can say that if we take the total, so in this case, let's put all of it back together. We have, S total over the, energy total. We're gonna be having 1 over T. Or, if we write better, we're gonna have T is equals to derivative of our entropy over, in terms of the energy, power of -1. Now, we do not write this as derivative of the energy as a derivative of the entropy, because it really doesn't make sense for us to write it like this. It makes sense mathematically, but not visually. So we want to keep it the best way we can. However, we made some assumption when we did this. We made the assumption in the fact that we have some things fixed. For example, we have that our change in particles is equal to 0, and that our change in volume is equal to 0. Because of course, if we change in the volume, then we're just going to increase the entropy without increasing the energy. And if we increase in the particles, we're going to increase the energy without increasing the temperature. So we're going to increase the entropy in a different way that we increase the energy. So here we have to say that N and V N is the number of particles, and V is the volume, are fixed. So this is exactly what we need, what we want. We can do a couple of examples with this. We can find the temperature, for example. So let's say we want to find the temperature of A in, I believe it's table 3.1, yeah, the one on page 86. So here, for example, it takes the value of, we want to find the temperature when our QA is equal to 12. So in order to find the slope, we find the points that are on either side. So when QA is equals to 11, and then when QA is equals to 13, and we said it's equals to the entropy, which is equals to 13, and then we have this minus 11 over, and then we take, of course, the values of our energy that are given. Sorry, here actually I should have written better because I'm getting confused too. So we have the temperature in this case, since we know mathematically it makes sense, just say the energy over the entropy. So in this case, for TA, when QA is equal to 12, we're going to have the energy, which is equals to, well, we're going to have 13 amount of energies, which is the unit of energy is equals to this symbol right here, minus 11 over, and then the value of the entropies at this point can be found from table 3.1 again. In fact, are 51.9 minus 45.4. And we have K, because K is the Kelvin Boltzmann constant. Okay. So here we're gonna have 2 over what is it? 51.9 minus 45.4. 6.5. So 2 divided by 6.5 is equals to about, and here we are again, our energy over our Boltzmann constant, 0.31 energy over the Boltzmann constant. So now, if we're given, for example, the value for a Boltzmann constant, and well, the Boltzmann is the same. For the energy, we can actually find the temperature of the solid. This means we can also find the temperature for B. Again, the energy of B, we can go back. So we know that the total, Q total, is equals to 100. So we're going to have to take these two values right here, and we find the opposite. So the values that with that, minus QA equals 100. So we're going to have, what is it, 100 minus 13. I don't want to say something wrong, and then everything else wrong. Okay, 87 unit of energy minus, we're going to have 89 unit of energy over, then we go back on the table for 87. I actually don't believe we're given, oh, yes, we are. Okay, so we have 172.7 minus 175.1, and here again, Kelvin Boltzmann constant. So we're going to have 2 unit of energy over 172.7 minus 175.1 is equals to, sorry, here of course, negative 2 over negative 2.4, Kelvin Boltzmann, so we get rid of the 2 negative. We're going to have 2 divided by 2.4, which is equals to about 0.83 unit of energy over Kelvin Boltzmann constant. Okay, so this is how we find the this is how we find our two values. And yeah, there's not much else to add to this. We would just need to find the value that we're given for this unit of energy. We are given that in our problem, which is 3.1, so we can just plug it in and find the temperature for each one of our values. And this is section 3.1, at least the first part. Then I start talking about a cell analogy, which I will cover in the next video.